out last time, you have to have 3 multipliers defined. If you use 27-bit arithmetic, I suggested last time you used 36, but if you use 27-bit arithmetic, that would be 3 multipliers. There's 87 multipliers, which means that you can do either 28 or 29 pipes that way, fully pipelined. However, there's another problem, and that is that you can't start the next iteration of a point until you finish this iteration because you don't know whether you're going to be doing it or not. And so the student suggested is do 4 points at the same time and alternate between them. So you're running one pipe across 4 points at a time. Very clever. You want me to identify you or not?
Yes.
Jacob! So, if you'd said no, that would have been funnier. But yeah, so you could have however many pipe steps you have, you could have a short buffer of points where all you really need to keep between iterations is the count. So you could go back and, so point 0 is here, point 0 is here, point 1 is here, 2, 3, 4, 5. So 5 points in the pipeline at the same time. After you clear this point out of here, you know whether or not you're going to run the pipe again for that point. Otherwise, you load a new point. Did I get it right?
Yeah.
All right.
You can also flash the pipeline at the compare stage.
You could do that too. The compare state, you could start over on the next one and just say, and if you don't need it, you throw it away. But yeah. So that's a clever 1 result per cycle version of this. Then you say, all right, should you have 3 multipliers per pipe? What if I just used 1 multiplier per pipe and made a sequential pipeline? So you're going to do a mult, then reuse the mult, then reuse it again, then do a compare. Now you can do a sequential pipeline. You can do 3 times as many solvers. But what happens to memory accesses then? Now you have 3 times as many solvers that are in contention for memory. So then it depends critically on how you're going to set up memory. If you're going to use a system that has contention, then your contention is going to be 3 times worse. On the other hand, if you use a system that has no memory contention, where every solver has its own block of memory, then that may not be a problem. However, with 87 solvers, you could start to run out of another resource. I'm just not sure how many resources. I don't think it takes much memory resource, but there could be something else that runs out. Can you ever run out of adders?
Yes.
You can when you run out of ALMs, because adders are embedded in ALMs. They add carry chains in ALMs.
What's that written underneath compare?
Yeah, that says clearly says compare. Let me rewrite it.
But what's the word under it?
Store.
Store.
Sorry. I have to slow down my writing rates consciously to make things clear. I had my freshman chemistry teacher held the fat chalk in between his fist like this so he could write faster because his fingers weren't strong enough to write as fast as he wanted to write. And he would fill about 14 boards per period. I can't do that. So, and it was moderately legible. So, another thing about pipelining is, another possibility is you do a combinatorial thing where you do 5 multiplies 5x multiplies two adds, or 3 adds, and a compare, all in one time step, so it's combinatorial, and then store. That takes more multipliers. You say, well, wouldn't that be faster than the pipeline? And the answer is, it's not clear. Because as soon as you put all of this stuff into one clock cycle, you may have to slow down the clock. So you may have to run this at 50 megahertz or slower if you have a set of multiplies and adds and a compare which are dependent upon each other in order. You can't do them all at once. They're not independent operations. You have to do them in order. And therefore the signal has to propagate through a big chunk of logic and it will be slower.
How do you go about testing stuff? Like what's the speed such?
So how do you go about testing the speed? Well, you can run the timing analyzer, the TimeQuest, and I strongly suggest that you figure out how to make a constraints file. Constraints file, as it says, TimeQuest and constraints files. And that will give you an estimate of how fast it will run. You can also program it up and see how fast it runs. Is it making mistakes or not? If you pipeline this with a fairly limited number of operations per step, then you may well be able to run the clock faster. You can at least run it at clock 100. You can get a 100 megahertz clock by phase locking the clock 50 input up to phase lock looping it up to 100, which is the preferred way to do it, because then you could say, I wonder if it'll run at 150. Click, and now you've got 150 megahertz. One change of one parameter. So you can choose the clock rate by using a phase lock loop. That's the correct way to do it.
What's the highest clock that you've seen before?
The highest clock that I've ever gotten any logic to run, and this was on a Cyclone 2, was I built a small CPU that ran at 250 megahertz. It broke at 300. I would guess that much of the hardware here will run at 200 megahertz. There are some speed. There's a data sheet which talks about speeds of multipliers. There's a Cyclone 5 data sheet which is a monster, but you can plow through the towards the end of the data sheet and give the estimated gate delays, multiplier delays, and so on. I don't think you're going to need to turn on pipelining in the multipliers. You certainly are not going to need to do that if you use 27-bit arithmetic, because that only takes one multiplier. If you use 36-bit multiplies for better zoomability, then it'll run slower because there's a sequential multiply add. But for this week, all you need is a solver running. Clearly, you're going to want to think about the structure because it will save you time next week. But you need a solver running in simulation. Next week, you need it running in at least 2 of them running on the FPGA and rendering to the VGA screen. The same day that you're going to get your final project talk. Any questions? I think last year, the maximum number of pipes we saw was 29 pipes, implying 3 multipliers per pipe. Any other questions on lab 2 or lab 3?
For lab 2, like RTL stuff, do you want us to show like zoom into like all the smallest blocks?
So, no, because there is a bazillion blocks there, and that was kind of left over from a simpler time. But you might show RTL of one of your solver patches, or maybe a piece of that.
Um,
Yes.
yeah, and what about Qsys? Do you want to show the full Qsys and like the audio subsystem? Whichever.
Did you change anything? Don't show it.
Because we got points off the first time for not showing it. So
Oh, then you better show it. Of course, it's a different TA this time. Who's grading this time?
Josh is on this one.
Josh is on this one? Ask Josh! So, today, but not only video. So, oh yeah, one other thing about lab 3, exercise 3, is that in the specifications it says there will be text on the screen. But I'm gonna modify that based on a student comment, and that is, if you define your own VGA controller, it becomes significant work to get text on the screen. I have code that does that. I went to the bother of writing a text ROM for the custom VGA. But I'm gonna say that if you roll your own VGA controller, you don't have to put text on the screen, you have to put it someplace else for timing. Okay? Slight modification. Well, let's talk some more about final projects, since a week from now you have to have some idea what you're gonna do. Anybody have a gasp? So, anybody have ideas about what they're gonna do? You gonna go for the vinyl?
Considering it.
Make a CD sound, make a nice digital sound like crappy vinyl. Yeah. It'd be fun. So I tried to outline some possibilities for just to sort of get you thinking about what the possibilities are. One is kind of an infrastructure thing, and that is to get OpenCL running on these boards. OpenCL is defined. I thought I put a link up here. Let me see it. Yeah. So if we go to the Terrasic site, Terrasic is the manufacturer that actually makes these boards. There's a whole bunch of users manuals. I believe that most of our boards are Rev F. But there is a set of software for running OpenCL. OpenCL is a high-level synthesis that looks like C function calls, but are linked to hardware running on the FPGA. And it would be interesting to get running. I think it is a big job, partly because you have to use a different compiler than you've been using. So every single tool in the tool chain will change. Another possibility in terms of infrastructure for amusement's sake would be to bring up a different version of Linux. There's a couple of versions that have desktops, including Ubuntu, Linux Ubuntu desktop. Ooh, that would be fun. Then you could have a GUI running on the VGA screen, low resolution, 640 by 480, pathetic resolution, but a GUI. Then the interesting thing is, how do you take computed output, graphics output, let's say a Mandelbrot set from the FPGA, and merge it with the graphics window system that's being generated by the HPS. The HPS is drawing all of the content of the screen then. But to be useful in this course, you'd have to be able to on your desktop with all the little widgets and stuff, you'd have to be able to punch out a viewport into which you could draw a Mandelbrot set from the FPGA. And it would be nice if there was some protection of windows against each other. In other words, the FPGA should know the boundaries of the drawing frame, and the HPS should know that that window is now under the control of the FPGA and not draw there. So that's a strictly kind of computer science-y system, Linux system kind of project. It could be fun. I'm trying to break these. There's some other project ideas down into something reasonable. OpenCL Mandelbrot render. It'd be fun to know if that was faster, slower. Improved automatic caricature by feature normalization and exaggeration. This is a strange scheme that identifies landmarks on a person's face, lip edges, eyebrows, eye edges, and then distorts them in ways that form caricature, basically taking any measurement which is different than the mean and moving it away from the mean. And there's a link on there that talks about the process. So those are some examples, more or less successful. Some terrifying examples. And then some idea of the landmarks that are used on the face. So that would be interesting. A ray tracer or GPU could be fun. Build a GPU for the HPS that lives on the FPGA. So the GPU takes drawing commands and executes them. I did a rectangle generator, 2D rectangle generator. That's the most boring possible GPU you could write. A triangle patch could be the input or the output from a 3D renderer. There's a whole subculture in taking obsolete machines and resurrecting them on FPGAs. These are connection machine and transputers were like dark ages parallel, highly parallel machines. Connection machine was 64,000 processors, as big as this room in the 80s. Josh?
You see Atmel Mega on FPGA, do you mean like just the CPU, or?
Yeah.
Okay.
No, so the CPU plus all the peripherals, the timers, the
Yeah.
interrupt. Getting interrupt right is interesting.
Yeah.
Apple to FPGA, of course. then perhaps something, I mean, I like physics on, as you could probably tell by the content of this course. I wrote a stochastic solver that gets below the level of differential equations and just counts molecules that are reacting. So it does a stochastic simulation of the reaction, where this for instance is the systematic differential equation version, and this is the stochastic version along with its noise. But maybe it'd be fun to do a gravitating particle system in which you fight by throwing gravitating particles around several suns at each other. So the paths become inverse square, arbitrarily complex, and chaotic. Oh, lab instruments. Nobody ever wants to do these, although they're pretty interesting. One group did a logic analyzer 1 year. A couple of people have done digital oscilloscopes. A good programmable signal generator would be fun with a GUI on the HPS.
What's a retina neural net? You have to pull it up. At the very top. Yeah, there. What does that mean?
So there's a real-time simulator of a biological visual system composed of a silicon retina and spinnaker chips. So that would be, there's quite a lot known about the structure of the vertebrate retina. And in principle, you could just brute force model the whole thing on a cellular level. And then see what it outputs. A complex impedance plotter, Bode plotter. Ooh, that'd be fun. That's some precision measurements of phase and magnitude of sine waves. And the whole thing there is more bandwidth. Speech is always interesting. Text-to-speech, speech synthesis, allophone synthesis, speech compression by linear predictive coding. That's a fairly compute-intensive process. It's not quite FPGA level, but it could be a part of a project that could be fun. Real-time speech pitch shifting is difficult. More DSP, head-related transfer function. This video clip is creepy if you listen to it on phones because it sounds surround you. If I just play it up here, you'll say. But if you played the video clip here on phones, you get the feeling of what head-related transfer function can do for you. Spatializes. Adaptive noise cancellation. How do those noise canceling earphones actually work? Cellular automaton music, fractal music. And then various kinds of musical instruments that I've looked in a lot more than some of these other things, so I have lots of references to them. Some image processing. Oh, software-defined radio. You can make a fairly adequate software-defined transmitter on this chip, which would be illegal. Unless very carefully handled. And what makes it possible is that the VGA output, no more VGA if you do this, the VGA output DAC can be clocked at 200 megahertz. That's enough. Various biological things. I like DSP, but there's lots of other things to do. Games are always in good taste. You've probably have you looked at any of the old final projects yet?
Mm-hmm.
There's going back to the really early ones is interesting because One of the first years was head-related transfer function. FPGA ray tracer. That's pretty competent. Why spheres and planes? They're easy in ray tracers. You see there's recursive shadows, recursive images of spheres on spheres. So you have to do some recursion of rays to make this go. A spectrograph which allowed you to produce a spectrum this way versus time this way. You could do a lot better now. This was that was 13 years ago. You could Fourier transform the heck out of this now and make a high resolution sonogram, which would be kind of fun. This game was insane. It was one person built this thing. Yeah. Does anybody recognize this game from someplace else? Do you recognize it from someplace else? Yeah. Every single entity on this screen is drawn in hardware. There is no software. There is no processor. It is mind-numbingly hard. These are all sprites that are in our M10K blocks that can be moved by moving their offset. It was complete, and it had a mouse support. It was completely 60 frames a second, seamless, no glitches. It was amazing. He was the guy I found asleep under the table one morning. I go in there and turn on the lights. There's nobody in the room. I hear this. Look, and you know, this body rolls out from under one of the benches. I think you've got fleas in here. I itch all over. Well, it turns out in those days we had wool carpet. He was allergic to wool. As far as I know, there's no fleas in there. Real-time edge extraction is now easy. This one was one of the weirder ones we ever had. Real-time, single image, random dot stereogram generator. So he could do stereo animation. If you stare at this with cross eyes, you'll see 3D objects. There is depth information and no contour, no line information. There's depth information which your brain will interpret as objects without having any edges. And it was moving in real time. It was pretty interesting. This is in the bad old days before I had a decent camera, so this is like a local MOB. I don't think I've ever moved it up to Facebook. I'm not sure, up to YouTube. I'm not sure. L Systems generates plants. So these are recursive drawing systems of curves, and can consume an arbitrary amount of CPU. So good. All digital FPGA lock-in amplifier. This is a phase lock loop amplifier. It could pull out signals with a signal to noise ratio of minus 80 dBs. Brute force search of a DES key space. Oh, what could possibly go wrong with that? He could break Windows passwords in a few minutes. Triangle CPU graphics processing unit. So this was, this is tricked up results. Ah, yes, there's the rabbits. Classic computer science rabbit, computer graphics rabbit. Kind of low res. Do better now. speaker recognition. This is not speech recognition. You don't care what the person is saying, you want to know who it is. How do you do it? You don't know. And neither do I. But you know when you're talking on the phone to your grandmother. How do you know it's your grandmother independent of what she says? It must be something about her physiology or anatomy. And probably it's partly speech patterns, it's word choice, and hesitations, and of course language and inflection. But it's also the shape of the throat, the shape of the mouth, the shape of the nose. And you can capture all that in what's called the Mel-Sepstrum, which if somebody wants to know more about, I'll be happy to talk, but I don't want to do it now. But it would be interesting, this project allowed the two partners to be able to discriminate A from B, the two partners, but it wasn't more general than that. Real-time face tracking, sound localizing robot, guitar synthesis. These aren't up on YouTube.
What is evolution tic-tac-toe? Oh.
I believe that this was an attempt to solve tic-tac-toe by learning. But I don't actually remember how well it worked. This one worked rather well. It was you know what green screening is? You all know what green screening is, right? The students made a green screen out of paper they found at the Canvas store, which is a crappy green screen, but it worked. So then they could project arbitrary graphics from the microcontroller, in this case HPS, onto the green screen and then superimpose live video over the top so they could be their own weather entity. And they got fairly clever with this, so you can do all kinds of. There was a setup. That was their sophisticated lighting arrangement. And so they used a video camera, Sony video camera, on a hockey stick. So this is a recursive example of students standing in front of the green screen, holding a screen in front of himself, showing, yeah, never mind. Showing, in fact, the one image back here and another image there. Fractal landscape. This is a process where you attempt to produce a landscape by repeatedly fracturing a structure, and there's a bunch of different methods for doing that. Oh, yeah, it's real-time cartoonifier. So they took the image coming in, they cut the number of colors down to about 15 or 8 or 15. They edge enhanced it and drew the edges on as heavy lines. And then sometimes cut the color out, sometimes left the color in, and made real-time cartoons, so to speak, of themselves. It worked pretty well. These are, Yeah, I must have. So a synthesizer, a very competent synthesizer, but there's some other sites. Of course, Hackaday, we all know and love, and has a number of amusing things you can search for using search terms FPGA, but there's also Hackaday.io, which has 2,300 results for FPGA. An NES on FPGA, FPGA Vision, Lattice FPGA Flex Module, nah. FPGA Board Hack, don't even think about it. FPGA Frankenstein is CW transmitter, yeah. All right. Open source FPGA, that's an FPGA written in Verilog for an FPGA. Makes your head hurt, doesn't it?
Why?
Because that way you control the bit stream and you can reprogram on the fly. OpenCV, so on.
What do you
Then
mean?
Hackster.io has a whole completely different set of FPGA projects. FPGA computer graphics, controlled robot arm. Oh, stochastic chemical reaction, that's me, yeah.
Oh.
Intelligent engine control unit. System, 16-bit system on a chip. Oh, it would be fun to bring up a RISC-V. RISC-V is all the rage these days. It'd be fun to bring up a RISC-V and get the toolchain running. There's synthesizable versions out there, I understand.
We've written one for the compound.
You wrote one.
Yeah.
Verilog?
Where?
Bring it up on the FPGA. Camera systems. So there's lots of examples. I think that another possibility might be a nice Roland 808 drum synth, simulated drum synth, with a control panel that's modeled on the HPS screen. I wrote a bunch of small CPUs if you find yourself interested in that. They tend to be back a ways on the earlier web pages. Hardware and processor examples. The shortest processor is 2 pages. 2 pages of Verilog. It's not very high performance, but it's easy to get running. I modified it slightly, and I wrote an assembler for it. So you can define constants, you can define data storage with a base address, and you can use a symbolic assembler. It compiles to M10K blocks. So you can make as many CPUs as you have M10K blocks, if you want. Don't use this 16-bit CPU, it's horribly, embarrassingly bad. I should take it down. So any questions about final projects? 5 weeks.
About the one where bringing up a new version
Say that, which, bring up a new OS?
on the system.
Yes, so you'd have to download the Linux image.
But that doesn't have an FPGA component to it. Doesn't meet the requirements.
If you do that, you have to figure out how to use the FPGA with the new OS. So if you're gonna bring up a Linux variant that say is a GUI, you have to figure out how to do graphics on the FPGA and merge it with the GUI. In other words, what matters here is that is the interaction between the two pieces. A good final project is gonna have an FPGA piece and an HPS piece that work together. Very occasionally we'll see FPGA only, and HPS only will not be allowed. That's a microcontroller project. So typically you're going to want to use both. You're going to want to use, in this lab, the most obvious way of selecting the center point for a zoom is use the mouse. It's like 4 lines of code on the HPS. You blast the coordinates across to the solver, to the planner. Or you probably can blast coordinates to each solver. And then the solver solves it. Anything else? Final project. So a week from now, a week from Friday. Come talk a lot, talk about final projects, kick ideas around. Again, whatever you're interested in another class, outside of class, use that as an idea, as the basis for your project. This doesn't have to be some abstract thing I think of. It's going to be much better if it's something you care about. No quadcopters. Nice.
Tricopters. Octocopters.
Hexacopters,
No flying devices heavier than a paper airplane.
so we can make a paper airplane for
An
us.
FPGA. That'd be some paper airplane.
Can the FPGA control a fan that flies a paper airplane?
That would be so.
That would be interesting.
That'd be pretty cool, yeah.
Because the payload required to get one of those boards off the ground is going to be significant. Maybe a little rocket assist unit. Take off.
I meant like a fan on the ground.
Oh, a fan on the ground. Oh. You know, there's this. The DoD is working on drones that are powered by a laser from the ground. What could go wrong? You got photocells on the drone, and you pump this big laser from the ground, it can fly indefinitely, of course. Unless it cooks. Any ideas? Any last minute ideas you want to float? So, you gonna meet Friday, or you gonna be in lab doing checkpoint 1? Checkpoint 1's pretty easy this week. Let's talk about DSP on